towel. I don't know. Anyways. Quiz number 3 tomorrow. Woo.
That's very spooky.
Yeah. Yeah, I should have had it last week. But then it wouldn't be on all the material. It is on chapters 5 and 6. But really, chapter 5 is really just 6.1, just drug out, which is the same as assignments 10, 11, 12, and 13. From Tuesday, you'll have been able to do most of 13, but not all of it. So after today, you'll be able to do all of 13 with a little bit of luck. So, all right. What I want to do today with you 4, because I think Tahira is on Zoom and she still counts, and it's still just Tahira here. With you 4 is I want to do a brief review of the concepts from Tuesday, because I know it was a video and I know I went a little bit over time there, but there's a lot to cover. And then I want to introduce 6.4, which is basically the same, but now for a two-way table. And then I've got an example going back to Tuesday's lecture. So another example from that I want to do at the end. So it gets a little bit weird, but I didn't want to push out the new material and just spend all day reviewing. So, although I guess I could have, but it's nice to go back to something simpler anyways. So in terms of review, we did 6.3, which was chi-squared goodness of fit testing. Goodness of fit testing. I will say that there are other chi-squared tests that we can do, right? But for us, just kind of referring to that formula sheet that you'll have, you have it for assignment 13. And so this is the formula sheet that you'll have on this quiz, right? For each assignment I've been adding, and for each quiz I've been adding whatever you need. You read it newspaper style. And I just keep piling stuff on here. So this would have been scary, just this at the beginning of the term. Now we've kind of picked away at it, but the chi-squared tests are down here. For us, we're just going to focus on goodness of fit testing and tests for independence. Okay. And so goodness of fit testing is going to be for one-way tables, and independence is going to be for two-way tables. Right, that's a little bit overly simplified from what we could be doing, but for this course, it's plenty. Okay, and so for review, because this is what we talked about last day, we did, I guess I could make it a little bit bigger. I know you don't feel like it, but this, so when I give you this, I feel like I've given you everything that you would need to solve this problem. I know that's not how it feels, but with enough practice, right? This is everything that you would need to solve this problem, right? Step 1, state your hypotheses. Step 2, do the test. Step 3, find your p-value, right? And then you can do your conclusion. Yeah? And so I want to just review. Scoot this over a bit here. Just going over the steps briefly, okay, because the steps are almost the same, or the steps are the same, but the procedure is almost the same for tests of independence as well. Okay. What's nice about chi-squared tests, even though they're kind of new, right? We're used to calculating Zs and we're used to dealing with Z scores, right? So now we've introduced this new thing, chi-squared. What's nice is we only do hypothesis testing with chi-squared. So we don't do any confidence intervals. right? And so we only do hypothesis testing for chi-squared questions. So that's kind of nice. And so goodness of fit testing, right? So that's this here, is applied to one-way tables. Now, what that means is we have one categorical variable with k categories. Okay. So goodness of fit testing is applied to one-way tables. And one-way tables, I feel like I'm just like linking these, I guess that makes sense. One-way tables means I have one categorical variable with k categories. Right, and k just generically is denoting the number of categories. Okay, why do we need k? We need k to find the degrees of freedom, so that's why I'm calling it just k categories. Okay. And so a one-way table might look something like this. All right, I have category 1, category 2, all the way up to category k. And then I have some observed counts, right, below in each of the categories. And then what I want to test is whether these observed counts follow the expected distribution of counts. Okay. And the example that we did in that video was the textbook distributions, right? So I, as a teacher, if I'm talking to the bookstore, they want to know how many books should I order in. I say 0 because why? They just jack up the price. And anyways, so I don't have them order any in, makes it easier. But in theory, right, they would say, okay, how many of your students do you expect are going to actually go out and buy the textbook? Who's going to read it online, right? That's more for me then. And who's going to print it off just from the web, which are all options that you could be doing with our textbook. So it's a textbook example from the textbook about the textbook. Whoa. All right. So we've got these observed counts, and are they the same as the expected counts? And that's going to be our hypothesis. Okay, so the observed distribution equals the expected distribution. You're going to want to make it more question specific, but in general, that's your null hypothesis. Okay. I'll just make a note here that this here is a one-way table. Because today we're going to talk about a two-way table. How do I analyze counts in a two-way table, which has one categorical variable here and another categorical variable here? But everything pretty well stays the same, including the conditions. So the conditions stay the same for both of the chi-squared tests that we do. I was going to say all, but I don't remember all of them. Yeah. So what's really nice is once we've got a handle on these conditions, these are the same for both types of chi-squared. Tests. Okay. So these conditions are going to apply today as well. Okay, the first one is independence, which means that all the counts that we're seeing, we have to they have to be independent of each other, or we have to assume that they're independent of each other. Otherwise, it's not going to work. Okay. One way that we can make sure of that is random sampling, just like before. And then we've got a sample size condition, which is basically the success failure condition, but now I have more than two categories, right? I don't just have a success and a failure, I have K categories, right? And so now the sample size condition is I have to have at least 5 expected cases in each cell, which means that in order to check the conditions, we first need to have the expected counts for each cell. So here, this means we need to find or need to calculate the expected counts before we can check the conditions. Before we can check the conditions. Okay, that's fine because we'll need those expected counts later anyways, right, for calculating our chi-squared. Okay, so in terms of kind of recapping our goodness of fit testing, right, I just want to talk in general, right, and I want to refer to just the formula sheet to show you that you have everything that you need. Okay, so step 1, once you've checked the conditions, which involves counting, calculating the expected counts, put on a fresh page here. Step 1 is you're going to state the hypotheses. Which I give you the null hypothesis. And with the null hypothesis, you don't actually need, I'm not going to give you the alternative hypothesis because it's just going to be the opposite. Okay. Right. The null hypothesis is that the observed distribution equals the expected distribution, which means that the alternative is the observed distribution does not equal the expected distribution. Of course, you're going to make that question specific, and it can get a little kind of hard to word sometimes, but just do your best, right? Referring to the variable that you're talking about. And if we talk about the textbook example, right? Does the observed distribution of textbook kind of access points, right? You can either buy the textbook, read it online, or print it from the web, right? And so we had 3 different categories. Does that observed distribution at the end of the term, is it the same as what the professor was expecting at the beginning of the term, right? That would be a question specific null hypothesis. Okay, so here you want to make this or make these question specific.
For the test tomorrow, is it in a similar format to the assignments, or are we gonna have to write it out?
I'm not going to make you write it out this time. I might make you do it for the final, but not for this quiz because we just saw it this week. That's not fair, right? So you'll have options. I know, that's so nice of me, right?
Same for the other tests?
Yeah, because they're just symbols. I don't want you typing symbols. It's too hard. Yeah. No, so you'll have them. Okay, good. Step 2 is when we do the tests, which is a fun way of saying calculate the test statistic, which is the chi-squared in this case. Oh, and I realized I didn't mention in the video from Tuesday, but this here. Oh, sorry, this, the observed minus the expected count is the residual. Right, the distance between the observed and the expected count. And then, let's see here, this is the squared residual. And did I run out of colors? Maybe. This is the Pearson residual. I only mention that because some of those tables get you to calculate the squared residual or the Pearson residual. So it's just kind of nudging you along in calculating the chi-squared test statistic. So what we're doing, right, is we're just seeing how far is the observed count from the expected count. I square it for two reasons. It makes it positive since I'm adding, I need positive values, otherwise it might negate it all, right? And squaring it amplifies the larger distances, right? If I have a large residual, then squaring that is going to amplify that distance, and that's what I want. So doing the test, these are all with counts, right? And so the observed count, the expected counts, all OI and EI are counts, right? Do not round expected counts. You want to keep those decimals because otherwise it's not going to add to the total. If you have an insane number of decimals, then you're allowed to round, but keep, at least 2 decimal places. Okay. So the expected counts come from the question, especially in the goodness of fit test. Whereas for tests of independence, we're going to calculate those expected counts, but regardless, you're going to have them from checking the conditions early on. Right? So in goodness of fit testing, GOF, because I'll define it once, goodness of fit testing. The expected counts come from the question. The expected counts come from the question. You might need to calculate them, right? But what we're expecting, so if I have 200 students and I'm expecting 50% of them to buy the textbook, how many am I expecting to buy the textbook? 100, right? So then you'd have to calculate them, but not, not really. I'll say may need to calculate. Okay. So once you have the chi-squared, step 3 is find the p-value. Of course, I introduced a new table, our favorite thing. All the tables you're welcome to use are, of course. But off the top of my head, I can't remember the format that the R command takes. So it's out there, but yeah. You might just enter all the data, which would take some time, but anyways, we'll use the table. All right, so finding the p-value. First, we need the degrees of freedom. And for a goodness of fit test, the degrees of freedom is the number of categories minus 1, which means that we're always going to have pretty low degrees of freedom, right? Even if we have 5 degrees of freedom, that means I have 6 categories. That's a lot of categories to be talking about, right? And so we're usually restricted to, you know, 5 or less degrees of freedom. The table goes for way, way more, right? The table goes all the way down to 50 degrees of freedom, which means you'd have 51 categories. That sounds insane. So for us, just to illustrate, I'm just going to take the first 5 degrees of freedom, bring it in. So the chi-squared distribution, the shape of it changes depending on what the degrees of freedom are. It'll always, in general, look something like this, right? So in general, it'll always be skewed to the right, okay? And then you'll have, I think it starts at 0. I want to make yeah, it'll start at 0, right? And then we've got this number line and the chi-squared is increasing as I move out, right? And so what I'm going to have is this tail area is going to be the p-value. We no longer have to deal with one-sided or two-sided because the p-value is always just the upper tail for chi-squared, so that's different. And our tests are always two-sided, right? Either the expected or the observed distribution is equal to the expected or it is not. Okay, so we kind of abandon that terminology, but the idea stays the same. Okay, so what we have in the table here, these are all chi-squared values. And if you kind of read one of these lines, let's say that you have 3 degrees of freedom, just as an example. Okay. What it's doing is it's moving out, starting at 3.66. It's telling you that the area in the tail at 3.66 is 0.3. Then it moves out 4.64, the area is 0.2, right? And then so it's just giving you some cutoff points. So what this looks like at degrees of freedom equal to 3, the chi-squared would look something like this. And so here's 0, and let's say 3.66 has an area in the tail of 0.3, 4.64 has an area of 0.2, 6.25 has an area of 0.1, and so on and so forth. Right. So what we do is we're going to be able to find a range for our p-value, or I also introduced the critical value approach, which we could have been using all along, where we say, okay, if I force the tail area to be 0.05, then the critical value approach says, all right, then my calculated chi-squared must be more than 7.81, right? Just beyond 7.81, because that means that the tail area is less than 0.05. So it's just 2 ways that we can get to the same conclusion. And just to keep it on the same page here, because I don't actually write down the conclusion, I just say same as always or something like that. Step 4 is the conclusion, which is going to be the same as all other hypothesis tests, right? You compare the p-value to the alpha level Or if you prefer the critical value approach, that's fine. You compare the critical value to your calculated value, and then you either have enough evidence to reject H0 or you don't. And then what does that mean in terms of the question? Okay, so that's our pretty long review of last day. All right, but that's all. We're going to build on that today as well. So you'll see it's not too bad. Bless you. 6.4 is chi-squared tests of independence. For us, right, because this quiz is coming at us so fast, right? If you have a one-way table in the question, then it is going to be a goodness of fit test, which is what we just reviewed. If you have a two-way table, it will be a test of independence. Okay, and so that's going to help. So tests of independence are for two-way tables, which look like this, right? We've got kind of some variable 1, which has category 1, category 2, category 3, let's say. And we have variable 2, which also has some category 1, category 2, category 3. They don't have to have the same number of categories. This is a 3x3 table. And so, but in general, a two-way table is just looking at two variables and how are they related? Okay. So I'm going to steal first this one because that's the one I want to do later. Wait. Okay. Just so I don't have to scroll back here later. Copy. Throw that down here. Now I can scroll. Because the textbook does explain the difference between a one-way table and a two-way table. So in case I haven't been clear enough, this might help. Okay. A one-way table describes counts for each outcome in a single variable, and a two-way table describes the counts for combinations of outcomes. So in the cross tabulation here of two variables. Okay. When we consider a two-way table, we often would like to know, are these variables related in any way? Which would be, are they dependent or are they independent? And so that's where the test of independence comes from. Okay. If you prefer to talk about, are the variables related? That's totally fine in your hypothesis. Okay. In my generic hypothesis on the formula sheet that you'll have, I think I wrote the variables are independent. Whatever. Okay. So the variables are independent, or the variables are independent of each other, or sorry, not related to each other. Say the same thing twice. So crazy, it might work. Okay. The conditions are the same, and I did realize there's a typo here. It should be EIJ. It doesn't matter for our purposes, but I don't want to spread misinformation in there. Be wrong. So I'll fix that. Yeah. in order to check the conditions are the same, right? We still have to assume independence and we still have to have a sample size that yields at least 5 expected counts in each cell. Okay, so even if it's a 2x2 or a two-way table, we still need those expected counts. Now, what I think is kind of nice is we calculate the expected counts. So it doesn't come from the question anymore. It comes from the row and the column totals as well as the grand totals. So once we do an example, it'll make more sense, right? But we'll be able to calculate the expected count in each cell. So that's gonna, wait. So loud. We need those expected counts to check our conditions, right? Without an example, it doesn't make sense to talk about the expected counts, right? So I'll wait until we have an example, but I will say the conditions are the same as for a goodness of fit test. In general, right, our hypotheses, so step 1, state the hypotheses. You're going to make it question specific, of course. The variables are independent or related. Oh, sorry, mix those up, not related, if you prefer. And then the alternative is that the variables are not independent, right? It's kind of how I like to word things because I like to have the not in there. But if you want to, you can say dependent. Or they are related.
Can you go back to the conditions?
Yes.
The first condition of the goodness of fit test is independence.
Yeah.
But we're also testing for
Independence.
independence.
Yes. I know, terrible, right? But yeah, that's fair. This independence is referring to the counts in each of the cells. Are they independent of each other? Right, so where I got these counts from, can I assume that they're independent of each other? Right, whereas the test of independence is looking at this variable, is it independent of this variable? So if we think about, we talked about how people vote and how they feel about global warming, for example, right? That was a two-way table, which we could do a chi-squared test of independence for. Is how people vote independent of how they feel about global warming or vice versa, right? Whereas the independence condition here is talking about, okay, well, the people that you're getting opinions from, right? How do you vote? How do you feel about global warming? Those we have to assume are independent of each other. So you're not just going out and sampling clusters of kind of group think. So yes, it is a little bit boggy, but this independence is for the counts and the test of independence is for the variables.
Okay.
Yeah. Okay. Okay. Step 2 is do the test, which means that at some point, right, we would need to have the expected counts. And so the expected counts are these guys. We first need to calculate the expected counts. calculate the expected counts for each cell. The I is for the row and the J is for the column. So E11 would be the expected count in cell 11. But don't worry, as long as you keep track of the row total and the column total over the grand total, then you're going to be fine. Then we can calculate this chi-squared, which is the same. It's the same calculation as before. It's the distance between the observed count and the expected count, and then we square that, and then we divide by the expected count, and then we add all those up. It's a little bit more work for a two-way table, right? Because we have more counts or more cells that we're dealing with, but that's just tedious. It's not hard, right? And I like tedious things. Makes me feel like I know what I'm doing. In step 3, we have to find the p-value. Now, once we have a chi-squared that we've calculated, right, then I need my degrees of freedom. That's the only new thing. And with a two-way table, it changes just slightly. But once we have the degrees of freedom and a calculated chi-squared, we can use the same table, right? And so we'll be able to use the same table, the chi-squared table. But we first need the degrees of freedom, which is going to be the number of rows minus 1 times the number of columns minus 1. Just in case it's been a while since you talked about tables, this is the number of columns, which we usually denote by C, and this is the number of rows, which is usually R. You'll have this formula on your formula sheet, so you don't need to remember this, but so R minus 1 times C minus 1, I just find it's a little bit cleaner to look at. And then, now that I have my degrees of freedom, right, again, I'm still going to need a huge number of columns or rows in order to get a big degrees of freedom, right? Even a 3 by 3 table would be 2 times 2, which puts me at 4 degrees of freedom. So I'm never going to have these huge degrees of freedom to deal with, right? But from here, right, then we can use the chi-squared table as before. So the change is really how we find the expected counts, how we well, not even how we calculate the chi-squared, right? The calculating the chi-squared stays the same, but the degrees of freedom is changed. So that's really the only adjustment that we make. And then, of course, step 4, the conclusion stays the same. Same as all hypothesis tests. With that vague summary, let's do an example. Okay. So I guess they introduced this data set in 6.23, but we don't really need it. We've got everything we need here, so I just went for it. It summarizes the responses of a random sample of college graduates and non-graduates on the topic of oil drilling. Complete a chi-squared test for these data to check whether there's a statistically significant difference in responses from college graduates and non-graduates, right? And what they're referring to is the responses with regards to oil drilling. Okay. They labeled the table here, college grad, yes or no, right? So that's variable 1 or 2, it doesn't really matter. Let's call this oil drilling. Oops. Right, they're either in support or they oppose it or they don't know, right? And our question is there a relationship between how people feel about oil drilling and whether they're a college graduate or not, right? So are these two variables independent of each other, or is there some sort of relationship there? All right. In order to check the conditions, right, we need to find the expected values. Okay? And so let's start there. In order to check the conditions, we need to find the expected values. And I'll say for each cell. So if we talk about this table, they gave us some of the totals, but not all of the totals. But we're going to need all of them. So we're going to need the totals at the end here, and I've got them 286, 306, and 235. And then the grand total is 827. So this is the grand total. The expected counts we find like this. For cell 1-1, just for simplicity's sake, right? The row total is 286 and the column total is 438 divided by the grand total of 827. So you can see how even though the row total is the same for this row, the column totals are not, right? And so you're going to have expected counts that are different for each of these, right? If these values were the same, then they wouldn't be different, but that's okay, right? In this case, they are. So what I like to do is sometimes I'll just kind of do the calculation and scribble the expected value beside this number, but it's our first time doing this big mumba jumba. So I'm going to give myself lots of room here and say these are the expected in support or opposed or do not know. Right. And then I'm going to have the yes group and the no group. But because I have to do, whoops, there it is, this calculation, right, for each cell, I'm going to give myself lots of room here. So then the expected count here is going to be 286 times 438 divided by 827, which, and I guess confession time, I didn't do these tallies, but I trust the guy who did them this morning. So now we all trust him. So if they're wrong, I don't think they are though. right? So now for those in support and no, right, the column, or sorry, the row total is 286 times the column total of 389 divided by 827. So the expectation here is 286 times 389 divided by 827. 134.53. That's a weird 3. Oh well. Moving on to the next row, 306 times 438 divided by 827, 162.07. Just to get a feel for how this is going, right? 154 is what I saw. I was expecting 151. I'm not too concerned about that difference so far. Things that I'm observing are behaving as I expected them, right? Same thing here, 132, I was expecting 134. That's still fine, right? So far, I am expecting to not be able to reject the null hypothesis, right? So that's what we're working towards. But then I get to 180 versus 162, and all of a sudden, I feel like maybe there's something going on here. Okay. So let's keep going. 306 times 389 divided by 827, 143.93. And the expectation here, 235 times 438 divided by 827, 124.46. And then finally, 235 times 389 divided by 827, 110.54. Notice that you don't want to round any of these values, right? As you add the columns as well as the rows, they should add to those totals that you have in the original table, right? We're just redistributing as if they were all independent of each other. Okay. So now we have our expected counts. That's great. First thing, I'm going to just scan. All of them are a lot greater than 5, so that's good. So then the second, or the first condition rather, is independence. So let's write these down. So the conditions, independence. I think it even said that the sample was randomly selected. Let me just confirm here. Responses of a random sample of college graduates and non-graduates. So these counts were randomly collected, selected, I should say, randomly collected, just on a whim. Since the sample was randomly selected, we can assume the counts are independent. Can assume the counts are independent. The second condition is the sample size condition. All of the expected counts are greater than 5, so the sample size is large enough. All the expected counts are greater than 5. So the sample size is large enough. So now we're ready to actually get started on this hypothesis test. So step 1, state the hypotheses. And what's that formula sheet? Right. I want you to, or I'm going to grab it from the formula sheet just so you can see that you can use it as a guide. Right. In general, the variables are independent. We want to talk about specifically what are these variables, right? And so the null hypothesis is that what I decided to say was the opinions on oil drilling are independent on college graduation. The wording can really bog you down. The opinions on oil drilling is independent of college graduation. I'm also trying to keep it nice and concise, but whether someone graduated from college or not. The alternative then is that the opinions on oil drilling is dependent on college graduation. And you can swap these, right? It's just how variable 1 generically compares to variable 2. So however you prefer to talk about these two, that's fine, right? College graduation is independent of how people feel about oil drilling. I just kind of went for one combo, but the opinions on oil drilling. But once I've committed to a null hypothesis, my alternative should just be the negative of that. Okay? So the opinions on oil drilling is I like to say not independent. Again, just because I like to have that not in there. But if you say dependent, that's fine. Is not independent of college graduation. And if you wanted to talk about there is a relationship between these two things, that's totally fine. Right, so there's some flexibility there. Okay.
I think in one of the like the last assignment, the one correct answer used the alternative hypothesis said that there's an association between the variables. Does that work too?
Yeah. Yeah. So independent, not associated, not related. Those are all options.
So I noticed like because I saw that associated where that like threw me off. I'm like, oh,
so
it makes sense because it's not independent, they're associated, right?
Yeah. So are independent, but I always get them mixed up. Are independent, not associated, or not related would be your null hypothesis. And then the reverse would be your alternative. Those are all fine. Confusingly. I like 1 and 2 sample proportions where we have kind of hard things that we use for our null and alternative hypothesis. I don't like these word hypotheses, but we've got to do it. Now, it's time to do the test, which means calculate the chi-squared, which I have here. Now, like I said, I like to have the observed and the expected counts kind of in the same place. So what I'm going to do is I'm just going to copy this. Cheating, I know. Just so I have those counts and then also copy this. Okay, so now I have my, my observed counts and my expected counts. So now I'll be able to, I've got these pre-calculated, don't worry. But I'm gonna write out what the calculation would be. And so the chi-squared that I've calculated is gonna be, and it doesn't matter, since you're adding all these residuals, you can go in any order, just don't mess yourself up. I like to just move across the rows. It seems logical to me. 154 minus 151.47 squared divided by 151.47 plus next one, 132 from 134.53 squared over 134.53. On to the next row, 180. This is where we started to get suspicious, right? Minus 162.07 squared over 162.07 plus 126 minus 143.93 squared. Obviously, you don't need to write these all out because you're not doing that kind of work, but I just want you to see where these are coming from. 104 minus 124.46 squared. 124.46. Finally, 131 minus 110.54 squared. Now, I have this one, I think. Let me crop top this. Whee! Oh, go bigger. There. Just be really careful when you're putting these in, right? Square and then divide, blah, 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 blah. But we get 11.457. So let's do 11.46. Because our table goes to 2 decimal places, it's safe to round to 2 decimal places. In general, you can just match the table. So the chi-squared, and what I want to do is just emphasize that this is the calculated chi-squared is 11.46, let's see. And that's from so the actual chi-squared calculation doesn't change. It's just a little bit longer because we have more cells that we need to deal with. But like I said, tedious is nice. Step 3, find the p-value. We're going to need the degrees of freedom to find the p-value. So that's on our formula sheet. So let's grab it from there. For us, right, the number of rows, we had 1, 2, 3 rows and 2 columns. So we have degrees of freedom equal to 3 minus 1 times 2 minus 1, which is 2 times 1. We have an itty bitty 2 degrees of freedom. So if I use the table then, I'll just nab the first 3 because I only need 2. What I want you to do is just now only focus on the 2 degrees of freedom. Right? All the other degrees of freedom don't apply here. the number of categories that you have is not going to change. So then you're fixed. Okay. So in that video, I introduced two different ways that we could tackle this, right? I can find a range for the p-values, which is kind of keeping with how we have been solving these problems, or I can find a critical value. We could have used the critical value approach for the Z tables as well, right? What Z makes this alpha level, okay? But I always find that it's a little confusing to introduce it all in the beginning. So this is my first time giving it to you guys. Okay, so what we do is we can use, let's start with the critical value approach. Only because that's the new one. And then I want to use the p-value approach for my conclusion. So the critical value approach says that what we're going to do is I am going to take my alpha level. Now, I don't think that this question gave me an alpha level, which means it's the default, right? 0.05. Oh, there. Statistically significant difference. There's no alpha level given, so we'll use 0.05. So I'll just make a note here. Assume alpha is 0.05. So what we would say then is, okay, if I force the tail area to be 0.05, the chi-squared that makes that happen is 5.99. So what this looks like is I'm forcing this tail area to be 0.05, which is the alpha. Oops, alpha is 0.05, corresponds to 5.99 at 2 degrees of freedom. Right. It's going to be different depending on how many degrees of freedom you have. But then what we're saying is remembering that this is just a chi-squared number line, right? So if my chi-squared calculated is larger than 5.99, then I have enough evidence to reject H naught. Okay. Our chi-squared calculated is 11.46. 11.46 would be somewhere here. Chi-squared calculated 11.46. We don't know what that area is, but I can tell you because it's further out into the tail, it must be less than 0.05. Right, so we're doing the same thing, just a slightly different way. So what we would say is that since the chi-squared calculated of 11.46 is, I was going to say larger, but I should say greater than the chi-squared critical of 5.99. Maybe I'll put that here, chi-squared crit. We have enough evidence to reject H naught. We have enough evidence to reject H naught in favor of HA. And then you could do your conclusion from there, right? So that's taking the place of comparing your p-value to your alpha level, but also your conclusion in terms of the null hypothesis. So then you would just state your conclusion in terms of the question. But for us, I want to use the p-value approach as well. Yeah. So the p-value approach, very similar, but now what we're going to do is we're going to take this 11.46 and I'm going to place it where would it fall on this number line? It would fall somewhere between 10.6 and 13.82, right? And so here, this would fall here, somewhere between those two. So we're just getting a range now, but remembering that the chi-squareds are increasing, which means the area in the tails is decreasing. So you want to read it from right to left, which gets kind of weird. But how I set up my p-value blurb is I write since first, and then I just do a bunch of notation here. Since the chi-squared calculated, which I'm putting in the center for a reason, is 11.46, is between two values. Those two values from the table are 10.60 and 13.82. Then the p-value, and I'm sure I confessed it in the video too, but I don't like inequalities, so I don't like thinking about inequalities. So I just make them match, which means that I need to write the smaller one first and then the larger one. So is between 0.001 and 0.005. That's kind of not as satisfying as having a real p-value, but it's enough. We have enough information here. It's somewhere between these two very small values, right? And so now that is going to be less than our alpha level, which we're assuming is 0.05. So step 4, our conclusion. Since the p-value is between 0.001 and 0.005, it is less than the assumed alpha level of 0.05. Which means I have enough evidence to reject H naught. Of course, our conclusions should match, right, from the critical value approach, which means we have enough evidence to reject H naught. In favor of HA. Therefore, right, you can reword the alternative hypothesis, or just say what the alternative was. Let's say in terms of a relationship, there is a relationship. Because I don't want to scroll up and see what I wrote before, between college graduation and how people feel about oil drilling. And how people feel about oil drilling. Ta-da! Chi-squared test of independence. Now, I did say I had another example for the goodness of fit testing, just to kind of emphasize that we are doing the same stuff. It's just the difference is one-way or two-way tables. And I want to do this cute example about rock, paper, scissors. We've all played it. All right, rock, paper, scissors, you choose whatever sign you're gonna play and then blah, blah, blah. For your statistics class project, you want to evaluate whether players choose between these three options randomly or if certain options are favored above others. You ask two friends to play rock, paper, scissors and count the times each option is played. And the following table summarizes the data. So because I have just one categorical variable, what sign did they choose? With three categories, rock, paper, scissors, this is a one-way table, which means I'm going to do a goodness of fit test. Use these data to evaluate whether players choose between these three options randomly or if certain options are, make sure to blah, 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 blah. I know, not helpful. In this case, we're not given the distribution, right? We're just saying, okay, were these randomly selected, right? What sign they were going to play. That's not a sign. Paper, scissors, rock. If they were randomly just chosen, that would mean an even distribution, right? Or a uniform distribution, right? And so here we have these counts, okay, with a total of, and I'm just going to give it to you, of 99. So if these were just randomly picked signs, right, then we would expect 33, 33, 33 in each category, right? Which would total 99. Right, so it's not in there, but it kind of is, right? And so sometimes we have to reach for it a little bit. So here, if the signs are chosen randomly, we would expect a uniform distribution. So sometimes the goodness of fit test, or often, is used to check against other distributions. Does this follow a normal distribution? Does this follow a geometric? Does it follow a Poisson? Does it follow all these other distributions? So that gets weird, and we're not going to do that. I max out at the uniform, which seems plenty. Okay. Now, in terms of the conditions, all right, independence. It doesn't say that, you know, you chose your friends randomly or anything like that. So what we're going to do is we're just going to assume the counts are independent of each other. We assume the counts are independent of each other. And the sample size condition, the expected counts are all 33, which is all larger than 5, so we're good to go. Each expected count is greater than 5. And I know I'm pushing it here. Fresh page. state the hypotheses. From the formula sheet, right, it just says the distribution the observed distribution is equal to the expected distribution. So let's get a little bit more specific here. The observed distribution of signs, wait. Is uniformly distributed. And the alternative is that it's not. And in the interest of time, is not. Doing the test is a lot easier, right, for a one-way table than a two-way table. Right? I've got these observed counts and my expected counts. And I am gonna cheat again. I think it was this one, yeah. My chi-squared here, this is the one that we're working on now. Right, 43, how far is it from 33? 21, how far is it from 33? 35, how far is it from 33? And we get a chi-squared of 7.51. So the chi-squared, the calculated chi-squared is 7.51. Oh, 5151, I guess. Too sloppy. Find the p-value. Find the p-value, which means I need my degrees of freedom, which is k minus 1. I have 3 categories. So I have 2 degrees of freedom. All right. I'm out of time. I know that. So I am going to just steal it from this morning and call it a day. Rude, I know. But everything from here on out, right? Once you have your degrees of freedom, it all stays the same. So then since your chi-squared, your calculated chi-squared is between 5.99 and 7.82, the p-value is between 0.02 and 0.05, which even though it's on the cusp, right? 5.99 corresponds to 0.05. And because it's 7 point something, it's not a concern, right? And it'll never be right on that cusp. Which means we have enough evidence to reject H0, and therefore the observed distribution of signs is not uniformly distributed. Chi-squared. If you have any questions, let me know. Otherwise, I'll see you tomorrow for an itty bitty quiz. Stop this recording here.